Welcome everyone to another session of this Gamma seminar. Today we have the second part of the super talk by Javier de Lucas from Warsaw. So whenever you want, Javi.
Hello and welcome back. If you didn't have enough super things last time, let's go for a second round. Okay, so more or less, let me just resume what I said the last time. And I was teaching some super geometry, super linear algebra, more exactly. And everything I did, it could be understood as a way to generalize what it's done in linear geometry to a new context in which every space has a decomposition into two subspaces in direct sum. One of each is said to consist of even elements and the other one consisting of odd elements. And it turns out that on this space, you can linear space, you can define different structures which somehow have to be compatible with the decomposition. So we start by linear spaces. We define superlinear spaces that are linear spaces with a decomposition as the direct sum of two subspaces, the space of even elements and the space of odd elements. Yeah, this is the conception of a supervector space. We define morphisms between supervector spaces that are just linear morphisms, but among these supermorphisms, linear supermorphisms, we can divide them into two main we could find two main classes: the class of the even ones and the odd ones. The even ones are those linear morphisms between superspaces that map even elements into even elements and odd elements into odd elements. And we have the odd morphisms between supervector spaces that are linear morphisms that map even elements into odd elements and odd elements into even elements. We define all the typical structures appearing in algebra, for example, the main structures such as algebras and things of the sort. And now we have to come to the definition of a superderivation. So here, what you have is that a vector superspace homomorphism, so A and A, they are supervector spaces with a decomposition into odd parts and even parts here and here. And derivation, a super homogeneous superderivation, it is a map, a homogeneous map between superspaces. And that means that it maps even elements into even elements, odd elements into odd elements. And apart from that, it satisfies the Leibniz super rule. So the Leibniz super rule is something that it is similar to the standard Leibniz rule. Okay, here you have the A. It must be an algebra to define a product. Indeed, it's a superalgebra. Please remember that superalgebra is a supervector space with a product in such a way that the product of even elements is even, the product of odd elements is even, and the product of odd and even elements, it's odd, or odd with even is odd. So when you have this derivation and you apply it to the product of these two elements with respect to the algebra structure of A, what you obtain is that this is the derivation acting on the first element times the second, and now it comes the new part. And the new part is that there is an extra sign with respect to what you could expect for a derivation. For a derivation, here you could expect nothing like this, yet like that, just the first element times the derivation of the second element. When you are dealing with homogeneous superderivations, what you have is that this product on homogeneous element is such that the sign depends on two things. on the parity of the element A and the parity of the superderivation. As always, as a linear map, it can have a homogeneous linear map, okay? It can have parity 0 when it's even and 1 when it's odd, so you will have something of this sort, okay? Yeah, so now this is the definition for a homogeneous superderivation, okay? And in general, you can talk about homogeneous derivations as the sum of two of these homogeneous superderivations. The set of superderivations on superalgebra A is denoted by the A, okay? There are several cases, several particular cases of superderivations as it's written down. So I will resume some of them. And for example, let us go back to our standard space, the space of differential forms. On M. And when you have the space of differential forms on M, please recall that you could divide it into two pieces. The even part, that there are all differential forms which have degree even, and those that have odd degree. This is the odd part, this is the even part. And now just recall that this is also an algebra, superalgebra, relative to the exterior product. Okay, that means that this is an algebra, you have a bilinear product, yeah, and this bilinear product on this superspace satisfies that when you have an even element and you make the exterior product with an odd element, what you obtain is an odd element. When you have two even elements with themselves there, it's even. When you have two odd elements on themselves, it's odd, and so on. So the product, the exterior product, is compatible with the composition. So these two things tell us that omega is a superalgebra. Also, it's supercommutative because when you have a 13 element belonging to the even part, well, in general, when you have a just remember that let's write it this way. This is P, beta is Q. So what you have is this. Parity alpha, parity beta. So what is this telling you is that is supercommutative. Means that even elements commute with everything and odd elements anti-commute with themselves. So this is a supercommutative superalgebra. And now derivations. You will have some mapping from this to this. And it will be a superderivation whether if you have 13, let us say theta 1, theta 2, there's homogeneous elements. Okay. So you will have that it is there will be an homogeneous superderivation if it satisfies this thing, that when you pick up the product, this will be d theta 1 exterior theta 2 plus minus 1, some number that it will be the parity of the operator D as a linear homogeneous homomorphism. And now you will have theta 1 exterior d theta 2. To be a superderivation, something of the sort, it has to be satisfied. Well, here it is still the parity of theta 1, yeah? There is an important thing in this expression that it used to happen in this super thing, is that you can see that here you have two things. And you can see that the order in here is first D and then theta 1. And what you had here somehow is first theta 1 and then it's D. In supergeometry, when the order of theta things is changes, it appears this factor with the parity. You can see that the same, exactly the same happens in here. And you will see that this general rule can be understood, certain categorical rule, whatever it means. That I will say what is a category afterwards, if I manage to explain it. It means essentially that when you change the order of certain elements in superalgebra, some elements, some sign of this type will appear. But what is important to me now is that I want to give some examples. For example, the stereo thing is linear, is homogeneous, and the parity is odd. The parity is odd because when the differential applies to even forms, can write, you will obtain that this is even, odd, sorry. Okay. And the other way around. I mean, if you apply to odd, it will be even. So it's a linear morphism and it's homogeneous because it changes the parity of homogeneous elements. And apart from that,
it's without the D's on the right-hand side, right?
Once again?
Without the differentials in the right-hand side.
Yes, sure. Yeah, you are right. Very well. And the thing is, when you have this thing, okay, apart from that, what you get is the famous rule. And this comes from the fact that since the parity of the differential is 1, because it's an odd homogeneous linear operator with supervector spaces, here you could write this and it would be 1, yeah? So the rule you know for the differential, isn't it, as way of saying that it is a superderivation. Okay, this is a way of doing so. And well, there are other superderivations. For example, the contraction, you can say something similar with a vector field, and it will be also an homogeneous linear morphism between superspaces. It will be also odd, so the parity of the contraction with a vector field is 1, and so again you will have something of this sort. Okay, also you have also the Lie derivative, blah blah blah, and you can imagine different things. For example, you could try to think whether this will be again a superderivation. Okay, you can think of it if it is or it is not. Okay, the composition of derivation, it is a derivation. It turns out that normally it is not. Okay, So you could think of the fact whether this thing is a derivation, for instance. Okay, indeed it will be equal to 0. And yes, it is a derivation. The thing is that this thing could be written in an interesting way. Okay, this is called a supercommutator. It means first this minus, and then the parity of the first, the parity of the second, x. Okay, something of this sort. And it can be proved that this is also a superderivation. It's a matter of calculations. Or for example, you could do this, the commutator between the differential and x. If you do so, it will be this minus 1, the parity of d, the parity of the contraction x and d. If you do this, this is equal to 1, this is equal to 1, so it turns out that this is this. And what is this? The Lie derivative. Indeed, the expression, the Cartan magic formula, is nothing but the supercommutator of the differential with the contraction with a vector field. And it turns out that this is a derivation that can be understood as a consequence that is a superderivation. When you do the parity of these two things, it can be proved that the parity is indeed the sum of the parity of the two elements you have. So the parity of the Lie derivative is the parity of the d plus the parity of this. So the parity of this is 1. The parity of this, well, it can be defined different ways. It's 1, so it will be 0. Yeah, that is how it should be. Because when you work out the Lie derivative, you have this, yeah? And there is no sign because the parity of the Lie derivative is equal to 0, and the sign you should write in here should be this thing, yeah? But the parity of this is 0, 0 times whatever is 0, minus 1 to 0, so it is, everything is fixed. So I expect that this was clear, okay? Because this is one of the very important things one who has to take into account in the following things. So here there is another example, and this is a very important one because you will find how to introduce the partial derivatives in terms of odd variables. And this is, I mean, algebraically, this is this seems to be a little bit, well, normal, but you can think about that with the Grassmann algebra. This is like making the partial derivatives, for example, with the differential of the coordinates. That it can be done. It's quite fun. Okay, so let us go back to this proposition. There exists only one superderivation on the Grassmann algebra of K, such that the superderivation of beta E applied to beta J is the delta Kronecker. So yes, let me recall you that KL, it can be understood like the Grassmann algebra of RL. I mean, this would be R some, I mean, the RL to 0 scalars, the vector space, 2 vectors, and so on, so to n vectors. This is the definition. This is a little bit weird, because it comes from the 80s, maybe, of the last century. But normally one would write something like this. It's not much more common. So imagine that you have one thing, okay, one superderivation, whatever it means. This is a superderivation. And now pick up the product of two elements. But due to the fact that these elements are scalars, they have index, they have parity 0. So if they have parity 0, they commute with everything with respect with the product, and this is just the derivation acting on the first. This is this. So since this is commutative, this is just this thing. Okay, but this is, on the other hand, is also this. So it means that this derivative of 1 is equal to 0. In general, any derivative acting on a scalar norm is equal to 0, like always it was. So now what you are doing is just to ensure that this acting on each generator will be the delta Kronecker. This is by assumption, okay? So if you do such a thing for every stereo product, for every element of the Grassmann algebra, that is the sum of different stereo products of elements of RL, you will be able to work out the expression. Indeed, you will see that if this is a product and there is beta I on it, the expression will be essentially 1 times the beta without that element, and if there is nothing, it will be 0. So let me write this way. Imagine that, for example, you have your Grassmann algebra will be beta 1, beta 2, the linear space R. Now the product, anti-commutative product, it will be just 2 because there is nothing else, yeah. And there is nothing. When you have 3 or more, for example, this and these elements anti-commute, this will be beta squared, unlike with differential form, this is equal to 0. So essentially, if you repeat this with this, you will see that it's also equal to 0. This is everything you have. Okay, because this is R2. So when you have this, you have the partial with respect with beta 1, for example, 1 is equal to 0. And then beta 1 is equal to 1 by assumption. Beta 1, beta 2 is equal to 0. And now if you have beta 1, beta 2, okay, since this is a derivation, it will act on the first one times the second. And now plus minus 1. And you have to take into account this is a derivation. You have that this derivation acting on beta 1 is an element of degree 0, it's a number, it's even. That means that this thing is an odd number, so the parity is 1, okay? And now you will have the parity of beta 1, that it is also 1. So you will have beta 1, beta 2, right? Beta 1. So this is equal to 0, whatever it is. This is equal to 1 for assumption, and this is beta 2. The beta 1 acting on beta, well, this is another element, you could do it. What you will find is that is minus beta 2. So you see, when you act on this, the beta 1, what you do is you drop the beta 1 element. And it, depending on the position of beta 1, you will have a plus or a minus at the very end. If the expression has no beta 1 like here, well, the result is a 0, and so on. So this is how this thing works. You can see that this expression in here, it can be proved to be determined to be a superderivation because it's just the Leibniz rules and the product on the previous one. So you will see that it turns out that essentially that it is true that this is a derivation and there is just only one. When you have the value of this derivation on the first and on the second thing, you will obtain that this gives you the value of the derivation everywhere else. There are many other results telling you that if you have a 13 derivation and you multiply, for example, for an element, this thing, it will be a derivation. Okay. But the thing about this derivation is that you won't have to take care of what is the degree of this thing, because it may happen that since the well, may happen. What you have to take into account is that when you add a 13 element to prove that this is a derivation, you will have to take into account that when you make the product with something, the parity of this will change. But anyhow, it can be proved that it is also a derivation. Okay. If you multiply by d2, also, if you multiply by beta 1, beta 2, whatever, it is also. This is if you take into account this thing, what you are saying is that the space of derivations on this space, okay, is a left module. That means that if you have elements of this space and you add derivations, it will superderivations, sorry, it will be a superderivation also. Okay. It also said that if you multiply them by elements of this Grassmann algebra, it will be also a superderivation. Okay. And there is a fun thing also is that if you have this thing, yeah, you will be able to classify every derivation as the direct sum of even derivations and odd derivations. So it turns out that if you have a Grassmann algebra and you pick up the derivation of this Grassmann algebra, it turned out that this is also another superspace, okay? Not only a superspace, it admits the product with respect to this element. It becomes a module, supermodule, is something that we will introduce in a while. Okay, and this thing, this object here, it appears in here, is very useful, is very interesting. Indeed, this thing is what it's going to give us the vector fields in differential, superdifferential geometry. Okay, this will be seen afterwards. So more or less, this is what I wanted to tell you. Okay, here. And after introducing this object, I mean, when you have a 13 Grassmann algebra, we more or less saw how the derivation on it are constructed. And we already said that this is a superspace. And we already said that we can multiply these elements by elements of elements of the Grassmann algebra, given to derivation, given the equivalent of a supermodule. And this supermodule is such that it admits two spaces, and the multiplication, it will be somehow compatible with the structure of the module. Okay, this is a very important example. So what I will give now is the exact definition of this module. So imagine that you have a superalgebra. Hey, like before, you can think that this is, for example, derivations, okay, because they have also a product. The product is the commutator, okay. Now, or you can think of a Grassmann algebra, okay, and now you have a vector superspace. Okay, you can think of it as, for example, before the derivations of the Grassmann algebra, and it is said that it's a left module, okay, if it satisfies the following thing. For, you know, always, like always in supergeometry, you have to take homogeneous elements of the superalgebra of the superspace. And what you have to do is just to make the product. The product satisfies the properties like in the with respect to the linearity of the module, of a standard module, okay? And the thing is, when you do it, the only thing you are asking is that one element of the superalgebra multiplied by elements of the superspace the parity of this must be the parity of the element of the superalgebra plus the parity of the element of the superspace. And that's it. That's all. This is a left supermodule. Okay. The typical example is a vector bundle over a manifold M, the Grassmann element. You can see that the elements of these sections are mappings from M to a Grassmann algebra. At each point of M gives you an element of the Grassmann algebra, the tangent space over the fiber of L at this point. And it turns out that this is a superalgebra. Okay, this is by itself. I mean, you can see that this is a space. You can divide it into odd and even elements, those that have expressions that are even covectors, section of covectors. The other part is sections consistent on odd covectors. Okay, and you have that you have the stereo product, and the even sections with even section stereo product is even without this odd, the odd is even, and whatever. Okay, so this is a superalgebra, and it is also a superspace. You can divide this into two superspaces, even and odd elements. And the thing is that you can use this expression that is superalgebra with this, that is a superspace and it's also superalgebra. You can multiply, and the multiplication of the algebra with itself, because this is a superalgebra, is compatible. I mean, it's like saying here that this is A, and the multiplication here is nothing but the multiplication on the module. So this, what you have in here, it is indeed an example of gamma lambda M module. Okay. The following proposition is what I said before, that you have a certain superalgebra A, okay, and you pick up the derivations on the superalgebra, they're A. It turns out that this thing in here is a superspace. You have the odd derivations, the even derivations, and derivations are the sum of odd and even, okay? And this is a superspace, indeed, has a decomposition as superspace. And also you can multiply elements of A of the superalgebra by the derivations, and you will obtain new superderivations. And this can be done in such a way that the module structure is compatible with the structure. So now this is a proof of this, but I don't want to get too much into technicalities. I will just write an example. So imagine that you have this thing, as always, differential forms, okay? So when you have these things, okay, these spaces, they are, they can be written in this way, where dx, this is a multi-index, normally is written like, I don't know, k, this is called to be k, yeah, u1, uk, and this belongs 1 to dimension of m, yeah. So the elements of this thing are these things. You can divide it into odd and even one. We have said this lots of times, okay? Never mind. So when you have such a thing, you here can define this fun thing, okay? And this is a superderivation. Yeah, you can prove that this derivation, it behaves in the standard way. I mean, if you this, it will be equal to 1. If you do this onto 2, it will be 0, and so on, okay? And it can be proved that this is indeed a superderivation, okay? There is another fun thing in that, and in this space, these things are functions. Okay, so you can also try to define these things. Yeah. So if you have here one function, standard function, this is the standard derivative of the function. Yeah, and with functions that are 0 forms, yeah, well, it works this way. Things of the sort, blah, 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 whatever. You can see that this is also and superderivation. It is even more. You can try to do this, but you have to understand that this is like a derivation on even elements, and these are odd elements, are different things. So this is supposed to be 0, and these things acting on this thing are supposed to be 0. Yeah. So it can be proved that every derivation on this thing can be written in this funny way. Okay. Is this thing, the sum, with certain functions here, with certain things in here, but these things here and this thing here are special, because this thing and this thing, they belong to these. They are differential forms. Okay, so it's kind of interesting because you are telling me that derivations are just the partial with respect to these variables, whatever the odd ones, and the multiplications by forms. Okay, this seems to be weird, but in supergeometry, the paper in one version of supergeometry, the functions are played by differential forms of things or sections. This is quite interesting that, for example, one Lagrangian, imagine it can be something of this sort. Okay. And now let me explain what is this. Imagine that you have TR, this is your base manifold, and you have a certain bundle here too on TR. And when you have this, you consider the exterior, the Grassmann element of it. Here. So what you have here is variables in this thing. When you have this, you will have two sections that generate everything, sections, okay? That generate all the space of the sections of this thing. And what you have in here, in this Grassmann algebra, the elements are functions depending on this, plus functions depending on this times θ1 plus another function that depends on it θ2 plus another function that depends on it θ1 and θ2. So the elements of these things are these things. I mean, in this model, functions are things that are these plus these plus these plus this. And this is the space of functions that you define. Okay. And normally it happens that this part is the classical part. For example, you have an harmonic oscillator, it will be 1/2 x squared, but things this. Okay. I mean, what you used to do in these super theories is that you will have zero part of function, and then you will have another elements. And these elements, these new functions, will be things that are sections of this Grassmann algebra. You will have the sections of the certain vector bundle of the base, and upon that you will be the exterior product of this thing. Sometimes the θ1, θ2 can be, as I told you before, it can be the sections, it can be differential forms of the exterior product of the differential forms. So in this theory, these are your functions. And if you want to make, for example, to describe the Euler-Lagrange equations for these, what you do is just, for example, to do things of this sort. Okay. But it may happen that for doing all the coordinates, you will have expressions like this with this partial, but the new thing will be things of this part. You see, the new variables, the new anti-commutative variables, okay, they will be like new function, new coordinates, but the difference is that these new coordinates are now anti-commutative. Okay, so as you see, the main thing in this is that the role played normally by functions now will be played normally by the Grassmann algebra of Grassmann bundle of a certain vector bundle. Okay, and this will be the base space of functions we are dealing with. And then when we have this, we will start doing things, partial derivatives and things like that. For example, in this theory, you can see that all derivatives you can have, they are the partial sum f of x, and here you have some function that depends on x point, θ1, θ2. You will have another function dependent on this. Another function depending on this. And another function depending on this. When I write θ1, θ2, it means that it will be θ1, θ2 on all the stereo derivatives, okay? So these are all derivatives, okay? These things you have in here. You see, this thing is a little bit like what you have in differential geometry. The only difference is that there are certain things that depends on variables, on new variables. There are odd elements, okay? But this is the usual stuff. And now the thing is that every theory, when you know how this works, every theory you have classical, Hamilton-Jacobi, or equilibrium points, or Euler-Lagrange equation, or symplectic geometry, or Poisson geometry, whatever. You can try to generalize it to the context where the main functions you will have, there are sections of this sort, okay? So everything you have done can be generalized. So, okay, so the things there are here is the following things that we have defined a module. And when you have defined a module, you can define also the dual supermodule, okay? So again, it's more or less the same thing, is that you have a certain superwrite a module as previously B with A, okay? A multiply on the right. Sorry, I am just checking. This is a left. It can be. No, okay. So the thing is that if this is a right module, the superdual is a left supermodule, and is a morphism between the module space B and the superalgebra A. There are mappings from A to B. And now the way of performing the multiplication is the following one, and is that if you have if you have a certain B and you have an element of the homomorphism from B to A, you can multiply these things by means of A. How? You apply this to B and you do this, okay? There is some interesting thing that here the module B is right, while the dual is left. Okay, this is essentially because you want to make compatible two things. And imagine that if you multiply B by an element of A on the right, you will say that this is this. Because when you write these morphisms, the dual morphisms, they have to be supermorphisms, okay, with respect to the multiplication on the right with B. I mean, if you have this thing, this will be the same as putting the exterior here. So in this way, when you multiply A with omega dot B, if here there is a lambda, you can always put the lambda here side, and this will be well defined. You have to think that if you do it the other way around, imagine that this could be a left module 2, and you have a third time lambda here, you can see that if it's outside, you had to put this outside, you couldn't know where to put it in here, to put it in here, because you know, if this has to be left invariant, this should be the lambda in here, yeah. But in the other way, imagine that omega lambda v, yeah. This has to be left amorphous of the module, it should be this. On the other hand, since you have a right module in the dual, you would like also to have this thing. And this could drive to this. So you see, you will have certainly a problem, because here it would be that. So somehow you have to fix everything to ensure that this is well defined. So the way of defining this properly is to ensure that when you have a left module, the dual one, or when you have a right supermodule, the dual will be left, and so on. So these are an example of these things. Okay, so the usual example of this is the space of differential form. So let us start. As I told you before, the usual stuff when you have a theory, a mathematical theory, physical theory, a mathematical theory. The standard thing is just you have a vector bundle, you have the exterior bundle, and your functions, super function they're usually called, is the space of sections of lambda. Okay, as I told you, for example, in one example, imagine that you have Tm, okay, and you have Tm times R2 as before, yeah. So what you will have is this thing. And here the sections will be fx dot plus gx x dot theta 1 plus x dot theta 2 plus j x dot theta 1 theta 2. These are your functions, your super functions. So the second thing is the space of derivations on here. Okay, this will be, as I told you before, the some function x dot theta 1 theta 2 partial x plus g x dot theta 1 theta 2 partial x dot plus j x dot theta 1 theta 2 partial theta 1 plus k x dot theta 1 theta 2 partial theta 2. And now if you want to perform this thing, okay, well, let me just tell you something. This is a left module. left module because you are multiplying derivations on the left. Okay. So if you have such a thing, then you have the dual. And this will be a right module. And it will be the dual, and it will be the sum thing, but the multiplications are on the right. Digital and so on. So when you pick up, you can do this. Okay, so when you do this, the thing that the differential force will be multiplied on the right, on the left, allow you to put everything on the right, on the left, and you have this thing that normally are defined in the usual way. If you have the dual of one thing will be 1, if not, it will be 0. And you see, the thing that the module of the vector fields and the module of the forms, they have the structure of the module on different places. It allows you to write this properly. It allows you to define these things in a good way. If you do this, on the other hand, no, you could have problems because, you know, how you do this? Yeah, you cannot put, if you start putting things out in some way, well, it would be, well, you don't have at first, you don't know at first how to do it. Okay, so it could be a problem. Anyhow, even if it's a problem, it could be solved, but I don't want to go into details because it's quite technical. It's that every left module can be understood as a right module, and every right module can be understood as a left module. I mean, that you can change the order of these two things. Okay, you can define the multiplication of this on the left. And essentially it's doing that by taking the homogeneous part and adding a certain factor. But anyhow, this is not the important thing, okay? So let me tell you what is written here is exactly like what I told you, that the derivation of the Grassmann algebra section is just the partial in terms of the the even coordinates on the odd coordinates, and the dual is just the differential forms, yeah, and things of the sort. So this is potential product of modules, and this is to define categories. Okay, so let us say this way. I think that for I could have things to explain for maybe several months on this. I gave a course on supergeometry a long time ago, and I have all these slides. Indeed, these slides are my slides converted by the student to give a talk, converted by me again to give again a talk. Yeah, so you could go till the very end of this thing and start applying these things. Yes, I think that he did not do really anything at the very end, because he did just forms. I mean, he did no example, yeah. Because the fun thing about it is that to look for examples of these in particular cases, for example, super harmonic oscillator, yeah, you pick up the super function, you start applying all the formalities, you know, symplectic contact geometry, super contact geometry, super Dirac geometry, and whatever. And the only thing you notice at the very end is that it's very similar to what it happens normally, but they are very difficult parts, non-trivial parts, due to the fact that the functions you are dealing with, they are not, the product is not commutative, because they are the section of the Grassmann bundle of a vector bundle. Yeah, so it's not commutative. But essentially, everything you do in the case of standard differential geometry has analog in this new theory, and there are lots and lots of things to do. Most of the things you can imagine of, they will not be available here, and they will have new details. So thank you for your attention. I think that today it's been enough. Thank you.
Thank you, Javi, for your super talk. I suppose that we'll be having more lectures on maybe super geometry next semester in the continuation of superalgebra.
Someone wants, I can do it. I mean, as much as I'm concerned, I have a work course about it, and with super Lagrangian approach, super Hamiltonian approach to super theories and all this stuff. So
We
I
saw
mean,
that we have 40 more slides, so
yeah, it will be there. There are many nice theories and things. The only thing, I mean, mathematically is a nice topic. Physically, the problem is that
no.
well, the main use is supergeometry, and so far no supergeometry has been found. So I don't know what's the point. I mean, for as I said, as a mathematical topic, it's interesting. There are some people dealing with it, but it's a particular one, quite particular one, and the physical applications that at the beginning they were thought to be the main point there are a little bit double.
That Lagrangian you wrote, it's something like a quantum harmonic oscillator or something like that.
It can be used for that. I mean, there is a theory dealing with super models, okay, of particles and whatever. But the thing is, normally, many of these things can be used in the quantum mechanics to find analogs. Yeah, but describe, for example, even differential forms, they are bosons, all differential forms, they are fermions, and describing things by means of these super function, this part often even or whatever, you will be describing certain quantum mechanical systems. And the zero part, the function, the pure function that appears, the standard one, you know, from your first years of differential geometry, it used to be a classical system. Okay, I mean, harmonic oscillator. And then you put some odd parts, some differentials to describe the quantum mechanical behavior. And when you describe the Euler-Lagrange equation, what you are trying to describe is essentially the Schrödinger equation or some kind of quantum equation for the model you are studying. So yeah, I mean, you can. Why to do it this way? Maybe I'm not a specialist, but I don't know. I mean, I know that there are works, I have read them, I know that it can be done, I know that they have application in quantum mechanics, but I'm not able to explain you why to do this way and not with the standard quantum mechanics.
Okay, and just one more question, because here we were surprised when you define a module over an algebra, when maybe the usual thing, if I'm not mistaken, is defining a module over a ring.
Or over a ring, yeah, but you know, it's a ring.
Yeah, I know. But for when you wrote and
well,
you said
it's not exactly a ring, because normally for rings you expect that it will be commutative. The thing is, here they are not
a commutative ring. Okay, but
it's
yeah,
it's a little bit more general than that.
Yeah, I know, because we were surprised because at some point you said that
I know, with the module,
because something was a module over itself.
Yeah, because
the functions or something like that.
I mean, you are used to define just on standard algebra, you start by vector spaces that are modules over fields, then you generalize over rings. Normally the rings, they use commutative. And the thing is that here is a little bit more general. Okay.
Yeah.
Because they don't. Well, it's just an algebra. I mean, this well, more general or not, depends on how you want to describe it. Yeah. Normally, it's the thing you are doing is as a vector space with a product does not need to be commutative. It's a little bit different. Yeah.
No, because I mean, for sure there are reasons for not doing it with a super ring, super commutative or something like that.
I mean, the standard example that it appears is the one I told you.
Mm-hmm. Okay.
Is the Grassmann bundle of sections for vector bundle. So you are used to define modules on it. This is the space you will be dealing with. So all the theories similar to modules is not exactly a module, as you said, and is defined on this object. This is what you have in mind. Okay. Indeed, there is a famous theory because well, this was much more general. I mean, normally the structures involved in supergeometry, they were very, let's say, they seem to be very general. But there was a famous theorem about Bachelor, that is a French woman, in 1979, who saw that every such a case in supermanifold, whatever that is a certain space, a sheaf of super functions, whatever it means, she said that it could be described by means of the space of section of the Grassmann vector bundle, basically. She said, every supermanifold at the very end, the space of functions is the space of sections of a Grassmann vector bundle. The problem is that that was in 1979. The problem is that in 1977, Kavensky, in the Department of Mathematical Methods in Physics, where I work, he proved exactly the same. But maybe the thing is that Bachelor was a woman from France, and Kavensky at that time was a man from Poland, and it's easier to become famous maybe from friends. I don't know how to explain it. The thing is that the result by Bachelor became famous, and the result by Kavensky not. Normally, all Polish people, or many, or indeed I do it, and I must confess that I knew Kavensky. He was working in Zaragoza with my supervisor and his collaborators, and I remember that I knew the theorem. I don't know that he was who thought it for the first time. And I know one Christoph who was working there, very nice, very intelligent, but I don't know that this was the guy who was doing the theorem I had read. So this was kind of fun that I knew who is just many years after that.
Okay, thank you, Javi.
Yeah.
Are there more questions, comments, remarks? No, no more questions. Everyone is super impressed, for sure.
Well, I expect that the topic is quite difficult, so I expect that more or less you understood.
I mean, it's difficult, but you began in the beginning, let us say, and it was not so fast. So at least here we could follow you most of the time.
I'll list that. Anyhow, as I said, if someone wants some theories can be generalized to this reality.
Okay. If there are no more questions or comments, we can stop now. Next week, Julia here will give a talk on slicings and
Hamilton-Jacobi theorem.
Yeah, but more. I mean, Hamilton-Jacobi will be more or less an example, something like that, or a particular case.
I need some introduction to Hamilton-Jacobi, and then I will proceed to defining slidings and maybe some applications to the theory.
Okay. So maybe we can stop now. Thank you all for attending. I will send you the certificate, Javi.
Give me 2.
Yeah, sure. And see you all next Thursday. Thank you very much.
Thank you.
Bye.
Bye.
Bye-bye.